Good morning and welcome back. So we will continue with our discussion on Rankine cycle. We will solve one problem, and with that we will close this Rankine cycle. Okay. So before proceeding into this particular problem, uh, so since this new restrictions are coming into force, okay, maybe from tomorrow onwards I will have to work from home. We don't have the official circular yet, but the government order, it is very clear that it should be implemented from 20th April. So most probably, I will have to work from home from tomorrow onwards. So if that is the scenario, then on Tuesday alone, so Monday we will have class between 9:30 and 11:15, or uh, sometimes it goes up to 11:30. On Tuesdays, if I have to work from home, we will start the class by 8:30. Tuesdays alone, we will have the class between 8:30 and 10:30. So this is for my convenience. Okay. Monday, we won't have any change in the schedule. We will have it between 9:30 and 11:30 or 11:15, whichever comes first. Tuesdays alone, we will have the class between 8:30 and 10:30. So on Tuesdays, be a little bit flexible. Okay, uh, so I'll let you know of the schedule tomorrow. I mean, about tomorrow, I'll confirm it in within evening. So once we have the official circular, I will let you know of this particular development. Okay, so Mondays there will be no change in our timings. Tuesdays alone, for my convenience, I would like to have it between 8:30 and 10:30 because I have to work from home. A small reshuffle has to be done so that I have to accommodate everything into uh, to put in its own position. Okay, so kindly bear with me on Tuesdays alone. So be flexible, be a little bit flexible. So I am saying 8:30 to 10:30. Sometimes if I'm not able to do so, maybe we'll have class only between 9:30 to 10:30, something like that, and we will have a compensatory class some other time. Okay, so Mondays I won't have any problem. Tuesdays alone, it will be a little bit. Uh, there will be a slight variation in our schedule. So for Tuesday's class, kindly check your WhatsApp group before joining the class. Okay, so let's proceed into this particular example. Okay, consider a reheat regenerative vapor power cycle with a feed water heater. Steam enters the first turbine at 15 megapascal and 600 degrees centigrade and expands to 2 megapascal. So they are talking about the first turbine here. Okay, so it enters at 15 megapascal and 600 degrees centigrade and expands to 2 megapascal. This is for the first turbine, the high pressure turbine. Then the steam is reheated to 600 degrees centigrade, okay, at the same pressure. So it is constant pressure heating. That is what we call as reheating. The steam for feed water heater is extracted from the low pressure turbine at zero point 0.5 megapascal. So it expands from 2 megapascal to before it completes its expansion at uh, so this will be zero point 0.5 megapascal where some extraction is taking place, and the remaining steam is expanded to 10 kilopascal. So it is like 150 bar to zero point 0.1 bar. Okay, so that is the total expansion in the low pressure turbine. Okay, so the working fluid experiences no irreversibilities, passes through turbines, pumps, boiler, reheater, condenser. Determine the fraction of steam extracted from the turbine, thermal efficiency of the cycle, mass flow rate of the steam if the cycle produces 120 megawatt. Okay, so before solving this problem, I want you to draw the TS diagram for this. So this includes reheating and regeneration, which means you will have two turbines and two pumps. So I'll give you 2 or 3 minutes time. I want every one of you to draw the TS diagram. I will call someone randomly and ask them to show their TS diagram. Come on, draw your TS diagram quickly so that we will proceed with this problem. Because drawing the diagram is more important. If you are able to draw it correctly, then identifying the value and solving it is going to be simple. Solve it quickly, come on. I mean, draw the TS diagram. I'll call someone. So have you done it? You should have done it by now. So let me ask Jagannathan. Jagannathan, have you completed the TS diagram? If so, you can share it with us.
So 1 minute, sir.
Okay. Just a minute. I think I'm not able to see because of the poor net connectivity over here. Yeah, now it is seen. Yes. Okay, you have drawn 1 to 2. Then is there a 2 to 11 or something in your diagram? From 2, is there a horizontal line, Jagannathan?
Yes, sir.
Why do you have this line 211?
Intermediate heating for more four.
Intermediate?
Intermediate pressure for 4 bars, sir.
For reheating, there is no extraction of steam during reheating, right? So there is no need for that process 211. We don't extract steam in reheating. Okay. Okay, fine. Okay, you can close your video. No problem. So let us see one more person. Let me call Nanda Kumar. Have you done your TS diagram, Nanda Kumar?
Yes, sir. Already sent. Sir, I'm unable to present the screen, sir.
Okay. So who else can we call? Harish Rajan doesn't come at all. He says some problem.
Sir, while presenting, it shows that you are not allowed to present.
Is it so? Okay, then
Yes, sir.
yeah, I think, yeah, I think now you will be able to do. Try now, you should be able to do it right now.
Sir, you are also presenting, sir.
Okay, so let me stop presenting. Hey, there is no number, then how can I check this?
Sir, 1 minute, sir. I have shared.
Okay, anyhow, please show that. That's sufficient. And there are a couple of errors also.
Sir, is it visible, sir?
Yeah. Okay, now try explaining what 1, 2 is 2, 3, 4, 5, 6, 7. Can you? What is 12S? Nandakumar, what happened?
Sir, I think 1 and 2 will be at the same line, sir.
Okay, that's fine. What is 12S? Okay, okay, you can stop presenting. I'll show you. I will uh, go to our presentation and I'll explain it. So let me say, so I have the not so straight. Let me try again. So we are talking about TS diagram here. We have the saturated vapor and the liquid line. So assuming it to be in the reheated state, so this is my point number one. And they are saying, so this pressure is 150 bar, 15 megapascal. So this boiler pressure is 150 bar and it expands to 2 megapascal, which is 20 bar. We do not know where it is. So let's assume that it is also in the superheated state. And there is a constant pressure heating back to the same temperature, 600 degrees centigrade. So that is point number three. And then from there, it is to zero point 0.1 var. But before that, some amount of steam is extracted at 5 bar. So this is your feed water heater. Okay. And after that, you have the expansion here, which is 5. Okay. And then in the condenser, this is your 6. Then you are pumping it to 7, and both of them join at 8. And there is another pump 9, which is the inlet to the boiler. Okay. He has drawn one more line from 2 over here to 10, and that is not needed because this 1 2 is only reheating. Here there is no extraction from point number 2. Okay, so reheating is taking the steam back to the boiler and heating it. inside uh, a set of tube bundles. It's not the boiler exactly, but a set of tube bundles which we call as some sort of a heat exchanger. Okay, so 2, 3 is your reheating, 3, 4, and it is at point number 4. Okay, so if you want, we can show that here. Take some other. So here you have 1 kilogram of getting diverted. So from 4 to the condenser and M1 to the feed water heat. Points. Okay, you should get the state points, and then so you can use Mollier chart. So from Mollier chart, you can get the values of H1, H2, H3, H4, and H5. All these values you can get from the Mollier chart. Okay, and then from steam tables, you can get the value of H6, which is HF at 0.1 bar. Similarly, you can get the value of H8, which is HF at 5 bar. Okay, these values you can get. And you have to be a little bit careful here. And the fraction of steam extracted from the turbine, that is the value of X4. No, not that. That is dryness fraction. What they are asking is fraction of steam extracted is M1. So you have to find out the value of M1. Thermal efficiency of the cycle, W net divided by heat supply. And here you have to be a little bit careful once again. Your W net will include W of high pressure turbine, you can say HT, plus W of low pressure turbine minus W of your pump 2 minus W of pump 1. All these put together will be your W net. And your heat supply will also have two entities. One is heat supply to the boiler, the other one is the reheating. So QB plus Q reheating. Okay. So don't be in a hurry to miss out any of these terms. So that will end up in a wrong answer. Okay. So you guys are still not very clear about drawing the TS diagram with the modifications. Okay. So that requires a lot of practice. So you can go through Mahesh and Raku. There are a lot of solved problems. Apart from that, there are a lot of exercise problems also. So you can uh, solve a number of problems so that you are thorough with the concepts. So is the Mollier chart visible to you, to everyone?
Yes.
Okay. So according to the problem statement, it is 15 megapascal and 600 degrees centigrade. Okay, so there is no problem because our Mollier chart is also in megapascal. So here you have got 10. So you have, just a minute. So here you have 10 megapascal and here you have got 20 megapascal. So this should be 12, 14, and in between 14 and 16, we should have another line that is your 15. So let's consider the 14 megapascal line, and then from there, uh, we can move on to, oh, sorry. So it is 15 megapascal and 600 degrees centigrade. Okay. So this is your 10, 12, and 14. Okay, so we have to move along this line till we reach 600. So this is your 600 degree centigrade line. Okay, so it intersects at this point for 14, and for 15 it should be somewhere over here, and that should be your point number 1. Okay, and that turns out to be 3,575. Do you agree? Okay, so for pressure P equal to 15 megapascal and 600 degrees centigrade, we get H1 as 3575. So H1 is 3575 kilojoule per kilogram. Okay, and let's see what H2 is. So for H2, it has to be expanded to 2 megapascal. So from point number 1, we have to draw a straight line till it reaches the 2 megapascal line. So this is the 2 megapascal line. So this is the 2 megapascal line. So I'm not able to draw that, I mean, very accurately, but that dark one over here. Okay. So I believe that you guys have taken printout of the sheet and you are drawing just like I am drawing. I hope you guys are also drawing it. So from here, so it is at this point, that is your point number 2, and that is slightly about 2950. So let's call it as 2975. So H2 is 2975. I'm not sure what the book answer is. I don't have the book by my hand and I don't have the solution also. So we shall just proceed as such. And from there, it has to move on to 0.5 megapascal. Okay. So 0.5 megapascal. So 0.5 megapascal is this line. This line is the 0.5 megapascal line. So from there, but before that, it should be a reheating, right? So if it is the reheating should take place at constant pressure line. So that should be the next step. And then after reheating, we have to move on over here. It is reheated back to 600 degrees centigrade. Okay, so that is the most important thing. So we have to go along this constant pressure line. We have to go along this constant pressure line till it reaches the 600 degrees centigrade line. So this is the 600 degrees centigrade line, and so this point is going to be point number 3. This is just lower than 3700. So let's say 3695. Okay, we will call this as 3695. Look at the TS diagram if you have any doubts. Okay, we have marked this 1, 2, and now we have gone along the constant pressure line to reach point number 3. The next step is you draw a vertical line from 3 to 4, and that is for a pressure of 0.5 megapascal. Okay, so now we have to go to the 0.5 megapascal line. So from here, so that is a straight line which is already there. So you travel across this straight line till it reaches the 0.5 megapascal line. So this is the 0.5 megapascal line, and this is your point number 4. Okay, and that is exactly on one horizontal line which is slightly above 3200. So let's say 3210. So we will call this as 3210. Are you guys doing this? Do you all have the printout of this Mollier chart in your hand? It will be there at the backside of your Steam tables. So let me finish H5 and then get back to you. So from 0.5 megapascal, it should be 0.1 bar, which means 0.01 megapascal. So from point number 4, we further drop till it reaches the 0.01 megapascal line. So 0.1 megapascal line is over here. This is the 0.1 megapascal line. So here we come. So this is your point number 5, and that is below. So between 2400 and 2450. So let's say 2425. 2425 kilojoule per kilogram. Okay, so these are the 5 different points that we mark from the Mollier chart. Okay, so now I'll stop presenting, and I want to know if you guys are really marking this with the help of the Mollier chart. How many of you are doing this actually? You can type in the chat box if you are looking at the Mollier chart. Do you have a printout of the Mollier chart? So if yes, you print on the chat box. Do you have printout of Mollier chart in hand? Nanda Kumar says yes. Who else? Vimal says yes. And the rest of the class, they don't have. So what should I do? Should I continue with the teaching or not? You should understand something. I do have soft copy of textbooks. There are a lot of textbooks. Thermal engineering by Kurmi is there. Thermal engineering by Onkar Singh is there. Thermodynamics by Sontag is there. All these textbooks are right there in my laptop, and I can simply share screen from those textbooks, and I can just go through things. But there is some effort that I am putting in to take these classes. Okay. So whether you are doing it or not, that is up to you. So there are two students who are following this up, and even if they are also not following, I just want to do my thing properly. But anyhow, it's a little bit of disappointment from my end to see that you guys are not working on a Molière chart. It won't take a lot of time to have a printout of it. It is there on the backside of your Steam table. Some of you don't have Steam tables at all, and all these are not very good signs. And I am not happy about it. But then it's up to you to do what you want to do. Okay, so these are the five points which you can take into consideration. And here, if you remember the definition of M1, the definition of M1 which we had seen earlier, it was like, I think H5 minus H6 divided by H2 minus H6. This was the previous definition that we had, but this definition won't work for this particular problem because the extraction of steam is not taking place at point number 2. It is taking place at point number 4. The mixing is not happening at 6. The mixing is now happening at 8. That is why it is very important to draw the layout and very important to draw the TS diagram. So unless you understand this concept, if you just memorize this formula over here, now you will be in trouble because the state points are entirely different because the definition has changed. The definition of the problem has changed. Okay. So now if you want to estimate M1, you have to write energy balance for the state point 8. So who is entering 8? So you have one entry from 4 and another entry from 7, and there is an exit from 8. Okay, so you have to take this into consideration for solving your M1. So let us write the energy balance for this. So you have M1 times H4 plus 1 minus M1 times H7, and both of them join together and give back H8 times 1 kilogram. So multiplied by 1, anything by 1 is just that term. So that is H8 simply. So you will have M1H4 plus H7 minus M1H7 equal to H8. Okay, and so M1 times H4 minus H7 equal to H8 minus H7. So M1 is H8 minus H7 divided by H4 minus H7. So this is the amount of steam that is extracted from the turbine before it goes into condensation, or this is the amount of steam that is extracted so that it goes into the feed water heater. Okay, so you can get the value of H8 by looking at HF at 5 bar. You can get the H4 value is already known from the Mollier chart, and what we don't know is H7. Okay, so Kaushik, you can help me with a value of H6 at 0.1 bar. I think this should be 191.8. Just check this, Kaushik. Is this 191.8 at 0.1 bar? And let me know what is the value at 5 bar. Are you there?
Yes, sir, checking. 1 second. So 191.8.
Yeah, that's H6. What about H8 for 5 bar? What is HF at 5 bar?
640.1.
640.1. Yeah, we saw this value also in one of our previous problems. 640.1. Okay, so we know the values of H8, H4, but we have to get the value of this H7. Okay, so for that, so before proceeding further, okay, so since the layout is also important, let's see what sort of layout we will get for this particular problem. Okay, so you have a boiler. So let me show it like this because we will have a reheater as well. So you have a boiler, and from the boiler we have the high pressure turbine. So this is your state point number 1. This is your state point number 2. And it is taken back to the reheater. And it is, sorry, so there should be a low pressure turbine. So the entry here is 3. Uh-oh. Okay, so let's say we won't do anything here. So part of it is, it has to be done the other way around. So this is from reheater, okay, and some amount is extracted to the feed water heater. So FWH, this is your feed water heater, and that which is extracted is M1 kilograms. Okay, and the rest is taken to the condenser, and from the condenser you have a pump, okay, so from the condenser to the pump it is 6. From the pump it is fed to the feed water heater, which is 7, and both of them mix and become 8. And this is your 9. Okay, so these are the state points that we have, though I am not able to draw it very nicely, but at least you will be able to get the picture of what it is. Okay, so this is the scenario that we have. So if you want to find out, so let us call this as WP2. So this is your pump 2 and this is your main pump 1. So your WP2 is VF times. So this pump is operating between the feed water heater. So P of feed water heater minus the pressure of the condenser. Okay, and so this VF is at condenser pressure, and I believe this value was 0.001010. Kaushik can check this. So this VF is at zero point 0.1 bar, which is 0.00101
Yes, sir.
meter cube per kilogram. Okay. So, and this feed water heater pressure is 5 bar minus 0.1 bar. Don't forget to multiply by 10 to the power 5, and you will get some answer over here. What is that you get? So it is 5 minus 0.1, sorry, 5 minus 0.1 multiplied by 10 to the power 5.00101. That gives,
49.9.
yeah, that, but that is in joule per kilogram. So we can write this as 0.49. It was 494.9, right? So let's say 495. So this is 495 kilojoule per kilogram. Okay, and this WP2 is between H7 and H6. So you already know the value of H6, which is 191.8, and WP2 is 0.495. So your H7 is going to be, so there will not be any change over here. So it is 192.295 kilojoule per kilogram. And now you will be able to estimate the value of M1. Okay, and efficiency, you have to find out the value of heat supplied and heat rejected. Okay, and heat supplied, you have two items here, the heat supplied in the boiler plus heat supplied in the reheater. Heat supplied in the boiler is H1 minus H9, and heat supplied in the reheater is uh, H3 minus H2. There is no problem in the heat supply. Okay, but when you go to heat rejected, Q out, that is taking place in the condenser, and don't forget to multiply by 1 minus M1, and that is H5 minus H6. Okay, and so your efficiency is 1 minus Q out by Q in. So this will give you the efficiency of the Rankine cycle. Okay. And one more thing is the mass flow rate of steam. So that's very simple. Mass flow rate of steam is what they have given is they have given you WT, sorry, W net. W net is I think 150 megawatts. What is that? 120 megawatts. They have said W net is 120 megawatts. You can simply find out W net as Q in minus Q out, and you will get some answer in kilojoule per kilogram. You can convert this also in kilowatt into 10 to the power 3 kilowatt. And if you want to find out the mass flow rate of steam for the entire power plant, it is W net. You can call this as W dot net because it is in kilojoule per second. Okay, it should be the other way around. W dot net divided by W net. Okay, kilojoule per second divided by kilojoule per kilogram, that will give you kilogram per second. Okay, and I think this you can do it on your own. Okay, so in Rankine cycle, what we have seen is the general layout is that you have a boiler, turbine, condenser, and pump. Okay, whereas we have also seen the condition for irreversibility, where sometimes your turbine and pump has got efficiencies, isentropic efficiencies, where the process is not purely isentropic. Then we have seen the modifications. We have talked about reheating. We have talked about regeneration, and then the combination of both reheating and regeneration. Okay, so with this, our discussion on steam power plant involving the Rankine cycle comes to an end. Okay, so with that, our Rankine cycle is over. But with whatever I have observed so far, you guys are still not clear about drawing the TS diagram. Okay, so please concentrate on it and see that you guys are able to be thorough with this. The next part of this particular unit is steam nozzles. Okay, and we have already done a little bit on this in our basic engineering thermodynamics course. Okay, and you know that nozzles are used to increase the velocity, and you have different types of nozzles. You have got convergent nozzle, you have got divergent nozzle, and you have got converging diverging nozzle, which we will see when to use when a little bit later. So if you look at this, in all the three nozzles, your velocity increases at the cost of pressure. Okay, which means your pressure energy is getting converted into kinetic energy. That is what happens in a nozzle. And you know that in a nozzle, there is no work being done. Work done is zero. Okay. And in most of the cases, we assume that this nozzle is adiabatic, which means heat transfer is also zero. And you can see that the inlet to the nozzle and the exit to the nozzle, both of them are almost at the same height from the ground. So the change in potential energy, that will also be equal to zero. Okay, so your pressure decreases and your velocity increases. The objective of the nozzle is to increase the velocity of the fluid flow that happens inside the nozzle. So if there is a decrease in the area, so if you look at this, the area decreases. The entry area is more than the area at the exit. Such type of nozzle is called a convergent nozzle. And here you can see that there is an increase in area. That's is called the divergent nozzle. You can see the area diverging, so it is called the divergent nozzle. And here you have both. There is a convergence, so there is a constant decrease in area or a continuous decrease in area, and it is at this region the area is minimum, and we call that as throat. And thereafter there is an increasing area, which is the divergent portion. And previously we used to have a subject called gas dynamics where we talk about Mach number. When you say Mach number is equal to 1, this Mach number is it is defined as velocity of fluid flow divided by velocity of sound. Okay, and when you say this is equal to 1, the velocity of flow is equal to the velocity of sound. Okay, so we assume because the area is minimum in the throat, you will have maximum area, maximum velocity in this region. The area is minimum and the velocity is maximum. So obviously the pressure should be much lesser. There will be more pressure drop here, and with that region is called as m equal to 1, which we call as sonic condition. Don't worry about this. So this is not the important thing. And when your flow is in the region m less than 1, we call it as subsonic condition. And when your m is greater than 1, we call it as supersonic condition. This we usually used to do as gas dynamics, which was a part of your regular course. But in this particular regulation, it has been shifted to the elective, so you won't have this course on gas dynamics. Okay. So this is about an introduction to nozzle. When to use convergent nozzle, when to use divergent nozzle, we will see later on. Okay. Flow through a nozzle from the steady flow energy equation. So if you remember the steady flow energy equation, we used to write something like H1 plus V1 squared by 2 plus G is at 1 plus W. This is equal to H2 plus V2 squared by 2 plus G is at 2 plus your heat. If you want, you can say if you have dot, then everywhere it should be multiplied or simply Q. And just now we saw there is no work done. Heat supplied is 0. The change in potential energy G into Z2 minus Z1 or Z1 minus Z2, that is also 0. So you can eliminate all these terms. And what is left out is H1 plus V1 squared by 2 is equal to H2 plus V2 squared by 2. This we have already done in our engineering thermodynamics. And we have said the velocity at the exit is greater than velocity at the inlet. Okay. If the velocity is greater than the velocity at the inlet, which means the square of the velocity will be much more greater than the inlet squared velocity. Okay. So if that is the criteria, then you can neglect this V1 squared by 2. It can be neglected. Okay. It is not that it doesn't have any value. This value is very small when compared to V2 squared by 2. So V2 squared by 2 is equal to H1 minus H2, or V2 squared is 2 times H1 minus H2, or I can say V2 is root of 2 times H1 minus H2. And usually the enthalpy, this is represented in kilojoule per kilogram, and therefore sometimes what they do is to convert that, they simply multiply it by 1000, so that this delta H, H1 minus H2 or H2 minus H1, whatever, so this value, root of 2000, I think this is 44.72. You can check that, root of H1 minus H2. Is this 44.72? One of you can check. Root of 2000. Okay, let's do that. We have a calculator here. So 2000 whole to the power 0.5.
Yes, sir.
44.72. Yeah. Okay. So that equation is also sometimes used in the formula directly. So that they have done to convert kilojoule per kilogram to joule per kilogram, and now the velocity, this particular velocity v2 is in meter per second. Okay. So this we have already done in engineering thermodynamics. This is just a recap of what we have done already. Okay. And discharge through an isentropic nozzle. Okay, so this concept you have to understand a little bit. So discharge through an isentropic nozzle. So when you say isentropic nozzle, the expansion inside the nozzle. Why do I use the word expansion? There is a pressure drop. It is that pressure drop or the decrease in pressure that is getting converted into increase in kinetic energy. Okay, so whenever there is a drop in pressure, when the pressure falls, we call it as expansion process. Okay, so the expansion in the nozzle is isentropic. That is what we assume ideally. Okay, why do I say ideally? The definition of isentropic is reversible adiabatic. None of the processes in nature are reversible. That should be always there in your mind. So the moment I say isentropic, I am talking about a reversible process which is not going to happen in nature. So that is an ideal scenario. That should be there in your mind always. Okay. And in the previous slide, I have showed you your V2, your exit velocity is a function of enthalpy drop, H1 minus H2. The entry to the nozzle is at a higher enthalpy, higher pressure. You know H is U plus PV, right? So this P is going to be higher and this U is going to be higher, and that makes H higher. And when you say H1 minus H2, it is at the cost of the pressure energy, so your pressure is going to fall. Okay, so I can say V2 is a function of enthalpy drop, and that enthalpy drop in the nozzle is equal to minus integral VdP. Okay, so if you look at a closed system, we used to call W as integral PdV, and for a recap, if you remember, if we have a cylinder piston arrangement, your piston can move up and down. So there is a change in volume. Your volume is not fixed. Only the mass is fixed. Mass is constant. That happens in your closed system, and we call it as W equal to integral PdV. What happens in a nozzle? Probably I could have drawn it the other way around. So this is my entry to the nozzle. This is my exit to the nozzle. What happens in a nozzle? Is there any change in volume? We have seen that this is your control surface, which means at the entry and exit, this is an imaginary surface, and this surface is real. The boundary is imaginary at the entry and exit, and the other wall side, you have got a real boundary, but this boundary is fixed, and so we call it as control surface. And the volume remains the same, so we call it as control volume. So here, there is no change in volume, but what happens to the pressure? There is a change in pressure. The entry pressure is more than the exit pressure. Okay, and because the exit pressure is lesser than the entry pressure, you call this as VdP. But to compensate for the decrease in pressure, there is that means the drop in pressure, we put a minus sign. So that is integral, minus integral of VdP. So this minus sign is given to compensate for the decreasing pressure inside the nozzle. Okay, so we can say that whatever increase in kinetic energy has happened, V2 squared by 2, that is the kinetic energy that we require, that is nothing but minus integral VdP. Okay, and we have assumed that the process is isentropic. Okay, they call it as isentropic, but they have taken the terms as n as a common term, where if your n is equal to gamma, that makes it isentropic. So you need not confuse this. As a generalization, this is n. But if you're taking it as isentropic, you can always replace n with gamma. Okay, so we have already done this, but because the term is slightly different, we can do that again if you want this. So VdP, we have minus VdP. Okay, and we have assumed the process to be isentropic, which means P1 V1 power gamma equal to P2 V2 power gamma equal to PV power gamma. Okay, we have taken something like this. So now what we require is something for V. Okay, so let me say PV power gamma equal to P1 V1 power gamma. So your V power gamma would be V1 power gamma divided by P, and my V would be P1 V1 power gamma divided by P whole to the power 1 by gamma. And this V can be substituted inside the integral sign. Okay, so integral VdP, I'm just neglecting, there is a minus over here. We are not taking this minus right now. Let's take that at the end. So that could be P1 V1 power gamma whole to the power 1 by gamma divided by P to the power 1 by gamma into Pp. And this term can be taken as constant on the outside because P1 V1 power gamma is constant whole to the power 1 by gamma integral of dP by P to the power 1 by gamma. And to make things simple and easy for calculation, we can say this is P to the power minus 1 by gamma times dP. So the moment you have the integral, it is between the limits 1 and 2, right? So keep that also in mind. So you are having P1 V1 power gamma whole to the power 1 by gamma here. And when you integrate it, you will have minus 1 by gamma plus 1 divided by minus 1 by gamma plus 1. Between the limits 1 and 2, which is P1 and P2. So you will have P1 V1 power gamma whole to the power 1 by gamma. And here you have, what do you have? So 1 minus 1 by gamma is gamma minus 1 by gamma. And in the denominator also you have got gamma minus 1 by gamma between the limits P1 and P2. So I can take this gamma by gamma minus 1 outside, and I can have P1 V1 power gamma whole power 1 by gamma, and inside the brackets I have P2 to the power gamma minus 1 by gamma minus P1 times gamma minus 1 by gamma. Up to this, is this clear? Okay, and now if I open the brackets, integral VdP, if I'm going to open the brackets, no change with gamma by gamma minus 1, P1 V1 power gamma is equal to P2 V2 power gamma. So for the first one, I can simply write this as P2 V2 power gamma whole power 1 by gamma multiplied by P2 times gamma minus 1 by gamma minus P1 V1 power gamma, sorry, gamma whole power 1 by gamma into P1 times gamma minus 1 by gamma. So if you expand this, you will have P2 to the power 1 by gamma. Okay, so I'll write that in two steps so that you can understand that P2 times gamma minus 1 by gamma minus P1 to the power 1 by gamma P1 P1 times gamma minus 1 by gamma. And if you add up the powers, it is gamma minus 1 by gamma plus 1 by gamma. So minus 1 plus 1 will get cancelled. Gamma by gamma is 1. So you will have P2 V2 minus P1 V1. And if you introduce this minus, then you have gamma by gamma minus 1. So this is for plus VDP. If it is for minus integral VDP, you will have gamma by gamma minus 1 into P1 V1 minus P2 V2. And if you want, you can take this P1 V1 outside and you will have 1 minus P2 V2 divided by P1 V1. Is this clear up to this? Okay. And I don't think I have given another space for it. This clear? Okay. So I'm not sure if we will be able to continue this over here. I didn't leave page for that, so that's a problem. What shall we do? It's not working here. So we said, so we were able to very light. So what we got here was minus integral VDP. This is equal to gamma by gamma minus 1 times P1 V1.
The screen is black, sir.
You are not able to see this?
No, sir.
Is it visible now?
Yes, sir.
Okay. So we said one minus P2 V2 divided by P1 V1. We got this. Okay, and what we said was the increase in the kinetic energy. This is equal to minus integral VdP. So gamma by gamma minus 1 times P1 V1 1 minus P2 V2 by P1 V1. Okay, and we also know P2 V2 power gamma is P1 V1 power gamma. So P2 by P1, that will be equal to V1 by V2 whole to the power gamma. Okay, so I can replace this V2 by V1, therefore would be, so if you invert it, you will have P1 by P2, but then if you remove the power, you will have 1 by gamma. Is that correct? Okay, so I can write this as V2 squared by 2 equal to gamma by gamma minus 1 P1 V1 1 minus P2 by P1 times P1 by P2 whole to the power 1 by gamma. Okay, so I will have gamma by gamma minus 1 P1 V1. So this is P2 by P1 1 minus 1 by gamma. So gamma by gamma minus 1 P1 V1 1 minus P2 by P1 whole to the power gamma minus 1 by gamma. Okay, and what I require is the velocity. So I can multiply this by 2. I'm just taking this 2 to the right hand side. So this is 2 gamma by gamma minus 1 P1 V1 times 1 minus P2 by P1 whole to the power gamma minus 1 by gamma. So V2 is equal to root of 2 gamma by gamma minus 1 P1 V1 times 1 minus P2 by P1 whole to the power gamma minus 1 by gamma. Okay, so this is the expression for the velocity. Is that clear? Any doubts in this?
So the expression for velocity can be changed, or
Changed in the sense?
so instead of v2 some other variable. So
I don't get what you are saying.
so the volume and velocity seem to be of same variable. So can we change the variables?
Oh, yeah. So that is why I usually put a small hyphen over it. Uh, yes, I didn't. I should have done that. I think now it should be fine. Okay, so capital V2 is velocity, and wherever I have represented V like this is specific, I would say specific volume or volume, no matter. Capital V is velocity. Okay, so shall we proceed further? Okay, so is the PDF visible now?
No, sir.
I have to stop sharing and then share it again. Okay, right? So now that you have the value as V2 equal to root of this. Okay, so we instead of n, we had taken it as gamma. In a general sense, it is given as n here. Okay, so that is not a problem. You know that you can replace n by gamma and gamma by n. It doesn't make much of a difference. So this is your V2. We have seen the derivation of this. And by definition, we know mass flow rate is A2 V2 by small v2. So this is velocity and this is specific volume. Okay. So we usually write m dot as rho A V, and we can replace this rho as 1 by V. So that is how it becomes AV by small v. Capital V is velocity, small v is specific volume. Okay, so your m dot becomes A2. V2 is this, and you divide it by small v. Okay, so that is 2n by n minus 1. P1 V1 times 1 minus P2 by P1 whole to the power n minus 1 by n. Okay, so A2 V2 by small v2, and this small v2 has to be once again taken inside. Okay, so how do we do that? So we have m dot. Are you able to see this whiteboard now? M dot is
Yes.
A2 capital V2 by small v2. So we don't disturb this A2 by V2. We simply substitute 2 gamma by gamma minus 1 P1 V1 times 1 minus P2 by P1 whole to the power gamma minus 1 by gamma. Okay, and if I want to take this inside the roots, you have A2 oh, it is erased everything. Oh my god. Can we undo this? Yes, we can. I should have used this eraser. Unfortunately, we don't have an undo option in life. If an undo option is there, it would have been very fine, but most of the time we don't have an undo option in life. What to do? In CBCS, the first day you take one staff, and unfortunately you have to travel with him till the end of the course. You can't change in between. If there is an undo, you can change, but now you can't. Okay, so to bring it inside a root, we make it as V2 squared. So this is 1 minus V2 by V1, no change. Over here, gamma minus 1 by gamma. I'm not sure why. So hope you understand this as minus. It does make it much more words. But if you use this, it's not very clear. Gamma minus 1 by gamma. Can I change the length of this line? I'm not sure. The thickness of this line. Okay. So now what we do? We know V1 by V2. V1 by V2 is V2 by V1 whole to the power 1 by gamma. Okay. And that will leave us with P1 by V2 on the outside. Just hold on a second. Oh, they have done it the other way around. So let's leave it right here. We'll take another page. So m dot is A2 V2 by small v2. So this is O to the power gamma minus 1 by gamma. Okay, this is what we have. And what they do here is they use the relation P1 V1 power gamma equal to P2 V2 power gamma. Okay, and for that V2 is taken as, so let's say V2 power gamma initially. So that gives P1 V1 power gamma whole divided by P2. So V2 is P1 V1 power gamma whole divided by P2 to the power 1 by gamma. So that makes this P1 by P2 times 1 by gamma multiplied by V1. So if we continue on this, m dot would be equal to A2 times this V2 is in the denominator. So you will have V1 in the denominator, but in the numerator you will have, if you invert it, you will have P2 by P1 whole to the power 1 by gamma. And then you have this entire term 2 gamma by gamma minus 1 P1 V1 into 1 minus P2 by P1 whole to the power gamma minus 1 by gamma. Is this correct up to this? Okay. And now we have to take this particular fellow into the, what is that? Into the square root. So if you take all this into the square root, leaving your A2 alone outside, you already have 2 gamma by gamma minus 1. So you have P1 V1, and I have V1 here in the denominator. So if I take it inside, it becomes V1 squared. And then I'm taking this P2 by P1 into the square root, which means it has to be squared. So it becomes 2 by gamma. Okay. And then I have 1 minus P2 by P1 whole to the power gamma minus 1 by gamma. Okay. So now what can I do? This A2 untouched as such. This fellow is 2 gamma by gamma minus 1. And this is P1 by V1. Okay. And then what we have is, if you take this P2 by P1 inside the bracket, the first one is 1, so it becomes P2 by P1 whole to the power 2 by gamma. P2 by P1 is same, so you can add the numerator for the second term, so it is gamma minus 1 plus 2 divided by gamma, so that make it gamma plus 1 by gamma. So P2 by P1 whole to the power gamma plus 1 by gamma. So this is what we have inside the square root. So this is your m dot, the mass flow rate. Okay, so this is the expression for the discharge through an isentropic nozzle. Okay, is this clear up to this? Okay. And there is one more thing which we have to do here. And I'm not sure whether this space would be sufficient for it. Let's try. What is the condition for maximum discharge? What is the condition for maximum discharge? You want m dot max. What is the maximum flow rate that can happen inside the nozzle? What we know is if it is going to be a converging diverging nozzle, the throat region, the lesser area that is going to have the maximum velocity, okay, which means where your pressure drop is less. As said already, the entry pressure is P1, the exit pressure is P2. So this ratio P2 by P1 is called as the pressure ratio. And this pressure ratio, when it is less, you have the maximum discharge. And that pressure ratio at the throat, that is called the critical pressure ratio. So not all P2 by P1 is critical pressure ratio. It is critical pressure ratio. It is called as critical pressure ratio. It is simply called as pressure ratio, but it becomes critical pressure ratio when that is estimated at 4. Okay, so that is the condition. So what is the condition for maximum discharge? So we all know in max, the condition for maxima is the first derivative should be equated to 0. But what is the derivative? So that is dm dot divided by d of P2 by P1. This should be equated to 0. So you have m dot here, and in that expression you have P2 by P1 here. Okay, so this particular thing should be taken into account for the estimation of the maximum discharge. So dm dot by d of P2 by P1 should be equated to 0. Okay, so d of A2 times root of 2 gamma by gamma minus 1 P1 by V1 times P2 by P1 whole to the power 2 by gamma minus P2 by P1 whole to the power gamma plus 1 by gamma. This entire expression whole divided by d of P2 by P1 should be equated to 0. Okay, and if you look at this particular term, this A2, this 2 gamma by gamma minus 1, this P1 by V1, these are all constants. They don't come into picture at all. Okay, they are constants, and if you take them and when you equate it to 0, they can be taken to the right hand side and they can be just eliminated from the term. Okay, so we need not consider these expressions. So what you can consider instead is d of P2 by P1 whole to the power 2 by gamma minus P2 by P1 whole to the power gamma plus 1 by gamma. This entire term divided by d of P2 by P1 should be equated to 0. Okay, so instead of taking the entire terms, all those terms becomes constant and they can be eliminated once you take them to the right hand side. Okay, so let us take one more page over here. So what we had was d of P2 by P1 whole to the power 2 by gamma minus P2 by P1 whole to the power gamma plus 1 by gamma whole divided by d of P2 by P1. this is equated to 0. And now let's start differentiating them with reference to P2 by V1. So what will you have for the first term? 2 by gamma times P2 by P1 whole to the power 2 by gamma minus 1. This is what you will have for the first term. For the second term, there is a minus in between. Oops, sorry. So you will have gamma plus 1 by gamma times P2 by P1 whole to the power gamma plus 1 by gamma minus 1, and this can be equated to 0. And because you have a minus sign, this term can be taken to the right hand side. So what you will have instead is 2 by gamma P2 by P1. So you can write this as 2 minus gamma by gamma, which is equal to gamma plus 1 by gamma P2 by P1. If you open the brackets for the power, it will be gamma plus 1 minus gamma. So gamma minus gamma will get cancelled and you'll simply have 1 by gamma. Okay? So if we try to take or keep P2 by P1 on one side, this is 2 minus gamma by gamma, and if I bring this P2 by P1 also here, I'll have minus 1 by gamma, which is equal to gamma plus 1 by gamma multiplied by gamma by 2. So what I will have is, if I equate or if I manipulate the powers, I'll have P2 by P1 2 minus gamma minus 1. That will make it 1 minus gamma by gamma. So this is 1 minus gamma by gamma, which is equal to gamma plus 1 divided by 2. Or I can say P2 by P1 is simply gamma plus 1 divided by 2 whole to the power 1 minus gamma by gamma. So this is what I get as an expression for the pressure ratio. And if this pressure ratio is there at the throat, and that is what we are saying, condition for maximum discharge. So this pressure ratio is called the critical pressure ratio. So this is called as the critical pressure ratio. So this expression is valid only in the region called throat where your discharge is maximum. So that is your P2 by P1. Okay, so we had an expression for m dot. So if we go to the previous page, so this was your expression. So m dot is A2 times 2 gamma by gamma minus 1. Is it P1 by V1? We will just check it. Yes, P1 by V1. This is P2 by P1 whole to the power 2 by gamma minus P2 by P1 whole to the power gamma plus 1 by gamma. This was the expression that we had before, and now you can substitute the value of P2 by P1 in this particular equation and you can get the value of m dot max. So your m dot max is a2 times. So no change in the first two expressions, 2 gamma by gamma minus 1, and you have p1 by p1. No change here. And now p2 by p1, this fellow is going to be gamma plus 1 by 2 whole to the power 1 minus gamma by gamma, and there is already a 2 by gamma outside. Okay, minus gamma plus 1 by 2 whole to the power. Just hold on a minute. Have we made any mistakes over here? Gamma plus 1 by gamma.
Gamma by gamma minus 1.
Yeah, that is what I'm looking at. See, when for this expression, and I don't know why none of you said this. So for this expression, it is 1 minus gamma by gamma over here. When it comes to the other hand, it should be gamma by gamma minus 1. So this expression, when it moves on to the right hand side, that should become gamma by gamma minus 1. So this is wrong here. I don't know why none of you said this. So the correction is, so this is gamma by gamma minus 1. Okay, so this should also change. So at least one of you or some of you are listening. So this is gamma by gamma minus 1 over here. So gamma plus 1 by 2 gamma by gamma minus 1 multiplied by gamma plus 1 divided by, somehow I should give 1 here. So this is gamma plus 1 divided by gamma. Okay, and so now you can manipulate on this powers, the power terms, and what you will get is a2 times root of 2 gamma by gamma minus 1. You have p1 by v1, and then what you have is gamma plus 1 by 2 whole to the power. So you will have 2 by gamma minus 1 here, minus of, again, gamma plus 1 by 2 whole to the power gamma plus 1 by gamma minus 1. Okay, so this is what you will have for the maximum discharge. Okay, and we started by assuming the flow to be isentropic, so we have gamma terms everywhere. Okay, but as a general expression, we always write this in terms of n. Okay, so if you look at the textbook, it will be in terms of n. So 2n divided by n minus 1, v1 by v1, n plus 1 by 2 whole to the power 2 by n minus 1 minus of n plus 1 by 2 whole to the power n plus 1 divided by n minus 1. This is the general expression that you have. Okay, so this is what you will be seeing in the textbook, right? So similarly, we will look at one, and that will be the end for today's class. Okay, so this is what we saw as discharge through an isentropic nozzle. And we have seen the condition for maximum discharge. And we said this is the condition. And we derived this. Okay, so here we said 2 by gamma plus 1 by gamma minus 1. Since we started with gamma, we just proceeded with that. As a general expression, you will have it in terms of m. And this is the expression that we have got. So you can further simplify that. You can further simplify that and you will end up getting this term. Okay. So you can couple these two expressions, n plus 1 by 2, and in the powers also you have the denominators as common n minus 1. So if you, so you will have this expression is entirely different from this expression. I think we have made some mistake over here. Okay, so which we won't be able to do it today, so we have to do it tomorrow. We have ended up getting n plus 1 by 2, but if you look at the presentation, the presentation says 2 by n plus 1. What we have got is n plus 1 by 2. So we have made some error somewhere. So we will check it up and we will start for the condition for maximum discharge once again tomorrow. Okay. So we will look into that tomorrow. So as I said, depending upon the circular that I get today, I'll let you know of the timings of tomorrow's class. Okay. And it seems like